r to the fourth. And now let's cancel out. What goes away?
Pies. Thickness. R squared.
And what I'm left with is 1/2 big M r squared. That is the formula for the moment of inertia for a disk or cylinder rotating about the normal central axis. Now, if you're looking at this and thinking, do you have to derive them every single time? No, you don't. On page 365 of the textbook, they have the formulas for common shapes. And pretty much any introductory physics textbooks may have a table like this. So let's just do a little plug and chug. Questions before I erase more? So I have a disk with a mass of 2 kilograms, a radius of 3 kilograms, not 3 kilograms, what am I doing there? 3 meters. Rotating at 4 radians per second. What is the kinetic energy of this disk? Step by step. That's 1/2 I omega squared. And I, for a disk rotating, I guess, say 40 meters a second, about its central normal axis. Normal meaning perpendicular to the face. So 1/2 m r squared. So this becomes 1/4 m r squared omega squared. That's 2, that's 3 squared, that's 4. What?
Joules.
Yes. Did you break down by units or think it's energy?
I looked at the K,
Yeah, that's pretty much the easy way of doing it. If you did it the longer way, that's kilograms. That 3 is meters squared, and then you've got irradians per second. Oh, oops, I forgot to square there. It's not 18. 72. Squared, and so kilogram meter squared per second squared is a joule.
So what units is the moment of inertia in?
Moment of inertia, you're multiplying mass times distance squared, so what would you guess?
Newton.
It's not a single word.
Newton seconds.
No.
Newton second square.
Newton seconds, that'd be momentum or impulse. It's just kilograms, meter squared.
And what does that mean? Like,
That would be if you wanted to stick it in something else, that's a joule second squared.
I mean, like, what does that mean in physically? Kilogram meter square? Or is it just some made up unit that just cancels out? I'm not made up, but like,
It's what the unit has, if you're dealing with SI units, it's just what the unit has to be. I'm not quite sure I can really.
I wasn't sure if there was a physical meaning for that.
I've never really associated physical meaning with the unit itself, other than it's just what the units are. I mean, like joules. Does a joule have any real meaning? I mean, we can artificially stick one in there of the energy. 1 joule is the energy gained if a 1 Newton force pushed on an object, 1 in the direction that it's moving, 1 meter. I mean, it's sort of an artificial definition. Now, limited inertia does have physical meaning, and we will get to that. But the unit itself, I would say just it is what it is. I feel that's unsatisfying, but that's where we are right now. All right. Other questions? All right, I'm gonna go grab some props. I will be right back. I'm just gonna let the recording go. All right. And need a ramp. I'll just use this view. All right. So the question is, if I race these at the same time, which will get to the bottom first? So we'll see if physics by democracy works. We've got the ball and the disc. All right, so who says the ball's gonna go down first? Would you like to field them to? I think the ball's a little bit heavier. I'm not a particularly good judge of that, but it's not blatantly obvious to me. Which one will get to the bottom first?
Here's the ball.
Going for the ball, all right?
Also the ball.
Be the same.
So tie and 2 for the ball, 1 for a tie.
You're talking about how long it's gonna take them to go down the sink line?
Yeah, if I race them, which will get to the bottom first?
Yeah. Do the same.
And I guess the other option is neither. Let's just assume that they will not burst into flames on the way down. All right. This will do.
As long as you naturally angle the cylinder perfectly, because obviously the ball will just naturally roll.
All right. And go. I think the ball is slightly ahead, but let's see if there's a table bias there. So the ball was slightly ahead. Like, were you thinking ball?
Less friction. This is a smaller point of contact.
The cylinder has more mass towards the edge of large R. Takes a
Okay.
little bit longer to accelerate.
So those are the same size. So if that's it, this does way more than this does. Would you make the argument that this would go faster?
Yes.
Jessica, Michael, who raised you, what wolves educated you on this?
I'll say no.
Say no?
Yeah, I'll say the cylinder go faster.
They're both cylinders.
The built-in.
The full, okay, the disc
The disc. There you go.
as opposed to the hoop. All right, so you're saying disc, you're saying hoop.
The same. I don't know.
And a tie. All right, so we've got. What's your best now? So we got the solid, we got the hoop, and then tie. So you were saying that, oh wait, no, you were saying that the solid one would go down first,
No, the hollow one will go down first.
hollow one. And just to see if there's some board bias there, or what I generally call board bias, this is slanted slightly differently. Congratulations. Why?
Because there's more mass on the outside, which means it takes more force to accelerate it, or it has more inertia. It doesn't want to spin as much as the other one, or it wants to stay where it is more than the solid one does, because there's more mass on the outside.
All right. So, in terms of formulas there, I would guess, and I haven't found, I'm not sure what the mass is, but I would say that this probably has a greater moment of inertia than this does. The formulas for the hoop mr squared, and for the disk both about with rotating about the central normal axis. So your theory is that the more mass that's on the outside, the slower it will be?
I guess.
You're not sure if you want to commit to that? Suppose we erase these. I think those are my only choices for groups. Oh, I guess I have that one too. Slightly smaller. So if I erase these three, which one do you think will make it down first?
Small.
Small.
Small one. And
Smalls.
why the small one?
Same reason for me. Because the more masses, more towards the middle.
Okay. This one seemed to win. Now it's going to be close. It's the relative thickness of this to the overall diameter or radius. You're judging by eye which one has a greater ratio. But recognize it's not the total moment of inertia that matters. It is, as you've been going for, it is the distribution of matter. So let's take a look at least one case of objects rolling down a plane, and show why the actual moment of inertia does not matter, but in essence, it's that number up front which matters. So we're going to do this from an energy point of view. We've got an object here, rolling object. Let's go ahead and make it a disk. So moment of inertia 1/2 mr squared. Excuse me. And I'm going to start it at rest. So as it rolls, I do have friction acting here. If there were no friction, it would just slide down the ramp. But so I need friction in order for it to turn. However, I am going to make the conceit that it is perfect static friction. In other words, there's absolutely no slipping whatsoever. So whatever point is touching the surface, that point is sort of stopped dead. Now, if we're looking at that, we're thinking about, wait a second, friction is a non-conservative force. How can energy be conserved here? Or how can we do this from an energy point of view? Well, if you think about it, that point that touches the surface here, that has the static friction acting on it, how far is, which way, talk about the displacement of that point. So if I got my hoop here, where is that point going next?
All the way to the top and then back down.
So in the immediate moment, when the friction's acting on it, which way will it be going?
In the opposite direction of its acceleration.
Pretty much nowhere at all, right? Or straight up.
Straight up is what I was going for. That the point basically comes down, it touches, and then lifts back up. Friction is acting this way. At this point, it's acting perpendicular to it, that's what I was going for. I have to think about the direction of acceleration, because we got linear and centripetal both acting there. So what I'm getting towards is that because the friction is perpendicular to that point of contact, it's not actually taking energy away. So if we look at the forces acting on it, we got a normal force this way. Friction's acting this way, we have weight acting down. And you make a similar argument with normal force, the fact that it doesn't move particularly far in that respect, or if you're looking at thinking of normal force as being sort of a macroscopic thing, it's going this way while the normal force is that way. Either way, normal force isn't doing much there. So I got 1/2 I omega squared because it's rolling. Potential energy associated with that conservative force?
MGH.
So since energy is conserved here, EI equals E final. KI plus UI equals K final plus U final. Oh, sorry. We have both kinetic energies involved, because not only is it rolling, but it is moving down in a direction. So there is a linear speed associated with it. So I have K initial, I guess K arc initial plus K translational initial plus U sub G initial equals K R final plus K translational final plus U G final. All right, we have this, what's gonna be, let's go ahead and use the formulas. So I got 1/2 I omega initial squared plus 1/2 mv initial squared